What I'm here to talk about is a new database. And it's a database that can support data-intensive applications that have a mixed workload, both analytical processing as well as powering applications with operational workloads. And the value proposition we provide to our customers is that typically across very many verticals, it's very difficult for companies to keep the decisions that they're making in the moment, meaning the data that they're using to derive any decisions or analytics is usually old data. It's coming from days ago. In fact, we ask people all the time in surveys, how old is the data in your reports? Simple question. And you'd be surprised what the answer is. 75% of the people say it's a day or older. Even in this day of streaming applications, lots of talk about Kafka streaming and Spark streaming and Flink. Today, it's still old data is being used to either learn on or to perform any kind of analytics. And the reason for that is very straightforward. That in the old architectures in databases, we bifurcated things into two basic systems. We bifurcated things into transactional or operational systems, powered by traditional databases on the high end like Oracle and on the low end like Postgres and MySQL. And then we extract, transform, and load through the ETL pipelines over to some other analytical framework. And that typically is at the high end Teradata or Netezza and perhaps some other kind of columnar database over on the OLAP side. But the problem with this is that these pipelines are incredibly complicated. These pipelines take a long time, and they typically end up being a big moat between what's being analyzed and what's being executed in the business in a real-time fashion. And we think that we're finally at a point where you can reach Nirvana, meaning that you don't need to have a bifurcated environment. You can actually perform your operational workloads, whether that's a mobile app, a web app, or some kind of social app, or something that might be even more advanced, and on that same data platform be analyzing in parallel. Now, the old school of OLTP and OLAP is prominent throughout enterprises, but many of you, if you've built applications in the last few years that are data intensive, machine learning applications, you've probably implemented something like a Lambda architecture. You guys know what a Lambda architecture is? No? So some of you do. So a Lambda architecture is essentially an architecture that takes the real-time data coming in and streams it or transfers it to multiple data engines at the same time. One data engine that can perform big batch analytics on it, typically something that might be on Hadoop using Hive or Spark or something like that. And then another layer that might be a speed layer where you can perform very quick operations and cleansing operations on the data, maybe look up that data. And then, of course, a serving layer that powers an application. Typically, people have used NoSQL databases like Cassandra or HBase. And there might even be a traditional relational database off on the side powering the application. And you can look at this diagram and say, why would anyone want to do this when you just look at the architectural complexity of keeping all these databases in sync? And there are benefits to doing that in the sense that you get access to your data that's real time to power the application, perform business logic, and at the same time, in the background, be constantly learning or performing aggregations and doing analytics. But this is very complex to maintain. And so essentially, if you could take all of those data engines and combine them into one data engine that is taking a streaming input, that would be Nirvana for the new Lambda architectures. And so these have fewer components, it's easier to synchronize, it's easier to maintain, and you have more application capability. So I'm going to make the case that there is a new kind of architecture that you can utilize for both combining OLTP and OLAP on one data engine, or creating what I'll call the Lambda R architecture for a relational Lambda architecture. And it's all being enabled by essentially two big technology trends. First it's the scale-out technologies that we see on Hadoop and Spark. And of course, it's the in-memory technology that we see with systems like Spark. And netting it all out, the system that I'm here talking about is the Splice Machine Relational Database Management System. And people don't really talk about RDBMSs anymore because they kind of went out of style when scale-out NoSQL came in. But they threw the baby out with the bathwater when NoSQL emerged and got popular because SQL has tremendous power for the data scientist, for the application developer. It provides a set of capabilities that for 25, 30 years people have leveraged for building applications. And those capabilities are still required. Instead of it being in the database layer, we see it ending up in the application layer in spaghetti logic. And that's not the best way to architect systems. So we built what we think is the best of both worlds. We retain SQL, full ANSI SQL, with ACID transactions, window functions, and all of the capabilities that you would expect in a true relational database. But we did it on a scale-out architecture. So what that means is you don't store all your data on one system. You shard the data across many different commodity servers. It auto-shards the data so that you don't have to think about how to split up the data. And it's elastic so that you can add more servers as your data loads, as your workloads increase. And it's incredibly price performant, meaning as you add servers, these servers are inexpensive commodity servers. You get the power of the parallelism of having all of these servers together, but without the cost of heavy engineered systems. And this does, through parallelism, give you 10x speed improvements or better. And it also provides you the ability to, in a very efficient way, and I'll show you how that works, perform the mixed workload of being able to perform operational short reads and writes that a real application needs in a concurrent fashion, keeping the database consistent, and at the same time being able to run analytics, aggregations, sorts, and all kinds of things that you would expect to do in a more analytical framework or on a big Hadoop-based system. So what are the kinds of use cases that people use a database like this for? Well, first, we see a lot of omni-channel marketing applications. What does that mean? You have a 360-degree view of your customer. You want to keep track of every interaction you have with your customer, whether that's a traditional set of orders that they're buying, whether online or in a store, or if that's interactions in social media or interactions with your mobile web application, or perhaps even just traditional calls in a call center. Keeping that into one unified customer profile and then being able to run campaigns that are both sort of batch driven, where every so often at some particular marketing drumbeat, you're reaching out to that customer audience either through social media or email, or trigger-based communications, where as soon as a customer does something, like purchases a product and gets them within a particular tier of a loyalty program, you'd love to be able to communicate directly with them and say, hey, just 50 more points, and you get all of these benefits in that very real-time, in-the-moment way. That's omni-channel marketing, and there are lots of systems that do omni-channel marketing. And one particular system I show here up on the slide is an IBM system called Unica. It's a third-party application. Unica is a system that was built by a startup company, bought by IBM, and typically customers use Unica with ETL systems like Ab Initio, reporting systems like Cognos, and we've got customers who actually compared what it would be like to run this application on Oracle versus running it on Splice Machine. And we saw 10 times price performance improvements on early versions of the system, and we think even better with new versions of the system at delivering this on a quarter of the cost. So it's about 3 to 7 times faster, depending on the kinds of queries. And this was directly against a pretty heavily engineered Oracle rack system. So what the takeaway is here, you can use Hadoop and scale-out architectures to replace traditional database applications that are running both large analytical workloads and needing concurrent transactions. We have other customers that are doing slightly different things. One customer is a financial services network, broker-dealer network called Cetera. They needed to also have a unified customer profile, but in the financial services world a little bit different, having a single source of truth that aggregates many different systems that have asset positions for those clients, and being able to calculate advisor commissions based on trades that are happening, and being able to do that with SLAs that get these reports out to the right executives at the right time was very difficult for them beforehand with all of these disparate systems. And they had a very large ETL pipeline and operational reporting mechanism, and now that's all being powered by the Splice machine RDBMS. And then lastly, showing you another kind of application, which is a very modern application, a machine learning application, where a database of clinical trials is kept, which has very deep biomarkers in it across many different types of information, ranging from clinical information to genomic information, and having that be trained in a set of machine learning models, decision trees, deep learning models, and then using those models to take new patients and match them against the clinical trials to determine which clinical trials are best suited for that particular patient. That's amazing, because what that does is it makes any particular doctor aware of the drug innovations that's going on around the world. This could save lives. This goes live in July. So lots of different use cases across marketing, financial services, life sciences. The unique aspect of an engine like this is that unlike traditional relational databases, where when you're running big analytical loads, even just big reports, your transactions tend to get backed up behind that analytical workload. And you often find yourself, even in the best operated scenarios, wondering, why are the screens getting so slow? Why can't I pull up this particular record? And it's because there's a big analytical report that's running. With Splice Machine, we've done something unique. We've created a dual engine, like the Lambda architecture that had the developer having to synchronize different databases that do different things well. We took that under the covers in our database. And we have one lane for transactions, where our transactions can just go take their own computational resources and run. And that takes place on a data engine called HBase. Some of you may be familiar with HBase as the key value store on top of Hadoop. And then when you have large joins, aggregations, groupings, and other analytical processes, they get run on Spark under the covers. And I'll show you how that works in a minute or two. But the whole idea here is that by having workload isolation, your operational workloads can operate quickly without being backed up by the analytical workloads, which means that as you increase your analytical workload, you won't see an exponential increase in the response times of your transactions. It should stay fairly constant. So that is the hope of, and the dream of, having resource isolation and being able to do simultaneous OLTP and OLAP workloads. And this is important for other new use cases that are emerging. Many of you have probably heard about the large data volumes that are produced by Internet of Things applications, other streaming applications. This is the kind of architecture that can be connected to Kafka event queues and flow through streaming systems like Spark Streaming and be able to directly run queries against streams on a continuous basis, because it can ingest data separate from the business logic. You can actually perform pretty amazing new kinds of applications that are streaming as well. So how is this thing built? We relied on 3 open source libraries. We relied on Apache Derby to provide us with the bones of a SQL processor. And we gutted Derby's storage layers and planning mechanisms to put in HBase as the persistent storage, and then incorporated many different distributed algorithms to enable us to take advantage of HBase's distributed architecture. And most recently, we've incorporated Apache Spark to execute the OLAP types of queries. And I'll show you in a few minutes how it works, but the basic architecture is very straightforward. Basically, you take open a connection via ODBC or JDBC to our database like you would with Oracle or Postgres. We create an abstract syntax tree of the SQL. We create an access plan for that. We optimize that access plan using cost-based heuristics and advanced approximation algorithms, sketching algorithms like hyperlog. And then what we do there is pick the right access path, the right join order, the right join algorithm, and the indexes that are necessary. And then we execute the queries either on HBase or in Spark, depending on what the proper execution path is. Some of you are probably familiar with HBase, but just to give you a quick little summary, HBase is built to reflect the same architecture as Google's Bigtable. It is an LSM tree architecture, meaning it is very much write optimized. It can ingest huge amounts of data. Data comes directly into memory. It fills a memory store. It puts the data on the proper server, and the servers are sharded, where there is a region of data that is sorted by a primary key on each of these region servers. And then when the memory is full, then what HBase does is flush the memory out to an indexed Hadoop file and an immutable indexed immute file that later, as more and more files are created, are compacted into one efficient immutable file. It's a very, very nice architecture for doing very short reads and writes in a completely scalable environment. And that's what we use for our main storage. Many of you are probably very aware of the recent popularity of Apache Spark. Spark is providing unmatched performance in many different computational areas, machine learning and others. It is an in-memory system. It can spill to disk when data sets are too large, so it doesn't fail if you can't fit in memory. It is very resilient to node failures, unlike Hadoop and HBase that replicates to provide resiliency. Spark does it with ancestry models, and it can recalculate computations based on knowing the lineage of a computation. And it's probably the most active Apache community right now. And it has an incredibly nice little set of libraries around it that utilize this technology. And so the way we architect it is very straightforward. Every physical node in a Splice machine implementation has an HBase region server and a Spark worker, and of course a data node underneath it for HDFS. And what happens is that we can automatically create Spark RDDs directly from HBase very, very efficiently. And we use the same bytecode that gets created for a SQL execution plan in each of these different data flow engines. So here's how it basically works. As you install, you basically are getting, as I mentioned, a region server and a Spark worker on each architecture. We distribute basically the executors out to each of the servers, and we don't use any MapReduce in order to do the distributed computation. It either takes place using Spark transformations, or it takes place using HBase coprocessors, so it's very efficient. So the way it works is that you take a SQL statement, you parse the SQL statement, create an abstract syntax tree. We optimize the plan, like I mentioned earlier, pushing predicates all the way down close to the data on the files, and then we unroll nested queries to make it very efficient. And then, depending on what the execution estimates are in the cost-based optimizer, if the result sets are very small, meaning you're doing a small read and write or maybe a small range scan, the bytecode that comes out of the optimizer and gets distributed to HBase through coprocessors and just executed in parallel on HBase's servers. If it's a large result set that is expected, perhaps like it's a 20-way join, it's aggregating with functions and it's grouping and sorting, that will get sent to Spark workers, and they will break that up into batches and use its fair scheduler to optimize and parallelize that process. So it's very clean, it's under the covers, and it allows you to use the right engine for the right computation. And as I mentioned earlier, we do support pretty granular resource management. So using C groups in Linux, you can allocate the proper CPUs, memory, and priorities to the Spark process and to the HBase process. So if you have a circumstance where you really want your transactions to be completely unaffected by any analytics, you might allocate your memory and CPUs accordingly. Additionally, Spark has a fair scheduler, as I mentioned a moment ago, and this is very flexible and customizable. So for example, we've set some fair scheduler pools. These are categories of priorities that you can assign queries to. You can assign user groups and roles to these fair scheduling groups. And essentially, the Spark's fair scheduler will allocate work to Spark workers according to these rules and these priorities. And you can extend that declaratively with XML in the setup files and through the interfaces that are associated with Spark that give you that really granular capability of controlling how the database performs based on the different queries that are submitted by the different people in the different organizations. And one of the other important things to be able to do is really see what a database is doing, especially a vast distributed database. Trying to understand, how it's breaking up tasks and distributing it to different platforms, different servers, is a difficult thing typically. And what we have is a query management UI that lets you see not only what's running now, but what's run previously, historically. You can see a timeline here showing different queries. You can click on them and see the actual query plan. And you can see the stages of a query execution. And it visualizes the parallelism, so you can see which part of a query is being executed in parallel and where there's a barrier where two pieces of parallel operations need to come together and be joined together by some function like a join. And you can dig in really deep into each stage of these query plans to see, individual tasks and actually look at granular resources like deserialization time for getting something off of the wire, how much garbage collection is going on, how many records are being either read or written to the data during this particular task. It allows you to get a very granular look at what the database is doing. And with these very large data volumes, this is very helpful to be able to tune your database, perhaps give hints to plans, or actually maybe create new indexes and key your database perhaps in different ways, and provides insight to the design for the DBAs and the data architects. So another really nice feature is in this Spark and Hadoop world, there's lots of stuff going on, and being able to coexist with all of the different libraries and computational engines that are being invented and being used is really important. And what we've done is created a federated query support. So what that means is, imagine you wanted to write a query that joined something in Splice Machine against something that might be in another data format out on Hadoop, or maybe even with Oracle. You can do that very declaratively. Down here in the bottom, you can see a little snippet of code where you can see a select statement where you're just declaring what the data types are in the external virtual table that you're connecting to. And that's all you really need to do in order to bring data in from other sources. And we already have, access to, for example, Amazon files or Oracle and other libraries out there. And we also fit nicely in the world of Spark and MapReduce, meaning perhaps somebody wants to run a large machine learning analytic. The features for that machine learning analytic may be stored inside of a Splice machine relational database. They may want to perform a little cleansing or a statistical routine on that. They can actually run this distributed job and do so accessing data consistently with transactional integrity out of Splice Machine, because we provide map output format classes. So we look like just a normal MapReduce job, or we declare to HCatalog, and you can run Hive against us, and you can run Spark jobs. It's really clean to be able to do that. And like I said, the database is really ANSI SQL. It's one of the only Hadoop-based systems that can run a traditional set of applications. One very large bank located here in San Francisco had code that they wrote years ago for a particular financial services application, and we were able to run it on our database in their tests. And almost all of the other databases that are modern query layers on top of Hadoop and Spark just don't have a sufficient amount of SQL yet. We're really trying to look at what does it mean to be a modern RDBMS. So we have to support a lot of capabilities. And lastly, I think the biggest innovation in terms of computer science that Splice Machine has made is specifically in supporting distributed ACID semantics, being able to support transactions. So what that means is that all of the ACID properties, atomicity and isolation and consistency and durability, all of these properties are maintained via an advanced MVCC architecture. The multi-version concurrency control architecture we use is standard snapshot isolation, meaning every write to the database has a timestamp, and no reader can see any writes that come after the timestamp of that reader. So there's no locks on reading. So the system, just like an Oracle system or a Postgres system works, it works on this distributed platform. And we leveraged some research that was originally done by Google in a system called Percolator. Percolator was a transactional layer on top of Bigtable. And that later was enhanced by Yahoo Labs and in a system called Ahmed. And we've brought some of the experts in from these projects, and we're really excited to have extended that research, in particular in handling really large transactions. Imagine somebody wanting to do 2 million updates and have that be atomically committed or rolled back. We can handle that, whereas some of the earlier research tried to keep all the deltas in memory, and sometimes that can be challenging if the transaction is too large. So that's some of the computer science behind our database. And more practicalities, though, databases are used by people doing business intelligence. Business intelligence is, of course, now a very robust industry. There's tons of systems out there, older systems like MicroStrategy, newer systems like Tableau or Domo or something like that. There are many, many different systems, even looking at Excel as one of these systems. We are easily connected to any of these through ODBC, JDBC drivers. And no matter what programming language you're developing in, again, ODBC, JDBC compliance gives you the opportunity to just write your application on top of us. We've got a great group of advisors ranging from the gentleman who ran the AMP lab in the computer science department at Berkeley, Mike Franklin, that's where Spark was created. Roger Bamford was the creator of Oracle RAC, one of the first employees at Oracle. Maria Namat was the founder and VP of engineering of Times10, one of the first in-memory databases, and then later took over all in-memory databases at Oracle when Oracle purchased Times10. Abhinav Gupta was a co-founder of Rocket Fuel, where I'm a chairman, and he was one of the earliest deployments of, he engineered one of the earliest deployments of HBase at a global scale for ad tech and being able to perform incredible numbers of ad bid impression evaluations in literally milliseconds. And Ken Rudin is the head of analytics at Google for search analytics, and formerly had that role of head of analytics at Facebook. And so great group of people, lots of good press, advanced management team. And again, just summarizing, and I'm going to open it up for questions. What we're all about is building a traditional RDBMS system. It's a SQL system. It's scale out. You don't have to worry about what data flow engine is under the covers. We worry about that in our optimizer, and essentially simplify the ability to make decisions in the moment by getting rid of the need of bifurcating OLTP from OLAP or having complex Lambda architectures. So with that, I'd like to open it up for questions.
Sure. So in your Splice machine, is OLTP and OLAP happens in your appliance? And if it is an appliance, do we still need the ETL to transform to your OLAP?
Very good question. So the question is it an appliance? And if it is an appliance, how do we transform or extract the data onto that appliance? And first, it's not an appliance. This is all software. There's no hardware involved in specialized hardware for us. We deploy in a couple of different ways. First, you can download it and put it on your own clusters, right? And it supports any of the major Hadoop distributions, whether that's Cloudera, MapR, or Hortonworks. And in some of them, it's very easily deployed as just a little one push of a button called a parcel that just puts Splice machine jars out on every box, and then you just connect. You start it and connect to it. With regard to analytical processing, if somebody has a boatload of data that they would like to essentially bring in and analyze, they do it in a variety of different ways with Splice Machine. Sometimes it's as simple as just pointing us to a Hadoop file that might have billions of records in it, and we just ingest it with a bulk import mechanism that uses every node in the cluster to simultaneously import. And we make sure indexes are kept consistent through our transactional integrity. Sometimes people will stream data in as it's being created through Kafka, for example, or another streaming mechanism.
In OLTP, usually you have all the normalized tables, right? So if you have, say, 1,000 tables in your
I see a question.
And if in the OLAP, you maybe drill down to, say, 40, 50 tables. So for that, you usually use your ETL processes.
I understand.
So do you still need to use it? Or?
Great question. Do you still need to kind of transform from a normalized representation maybe into a star schema or something like that? And I say that that's definitely use case specific, because sometimes the parallelism that's afforded by our architecture is fast enough where you can keep the data in the operational framework and just query against that. Sometimes you do want to convert it over to a star schema to afford yourself some of the simplicity that gives you in query processing, and even just helping the data scientists think that way. It's useful to do the transformation. But the point is, then it's really, you're getting rid of the extract, right? And you're getting rid of the load. You just do the transformation. So it's just T, not ELT or ETL, because it's all on the same platform. So you do have different people doing different things.
So my follow-up question to this is, how this is different from Apache, Gridlock, because Grid essentially does querying across all your data sources. Hadoop, NoSQL, relational databases, file system, JSON, Spark, format, name it, and
Sure.
do it. And Cadet is OLAP, which is open source. So do you have any?
Yeah, I can, in a nutshell, there are many things different between the systems of how they work, but the principal difference is that none of those systems can simultaneously do transactions. None. And if you have an application where you have multiple users hitting the applications at the same time with concurrency, and you want to be able to make little reads and writes and changes and updates, those systems will simply not work. They don't have the MVCC that provides the transactional integrity. Many systems are available for analytics only, but if you really do have just a data set that maybe gets updated once a week, you're going to perform some big machine learning analytic or some scoring function on it, many different systems may be appropriate, like Drill or even columnar databases like Vertica. But if you have a living, breathing database application where data is changing on you in near real time and you have concurrency going on, you need an ACID compliant database in addition to your analytical workload, and that's what we've attempted to focus on. Any other questions? Yes?
So in your systems, it looks like the way you deploy is basically making sure a Splice machine on every node, right? So is the Spark in there is a standalone node or is it a node? What kind of node?
Great question. So the Spark system is controlled by Yarn, and we can allocate to the Yarn processor. And we've also done something which is, your insight is keen there, because Spark typically is architected to have one Spark context that is aware of the resources across the whole cluster. And we've engineered a unique ability to use a remote Spark context, so that any one of those nodes can find the resources and dispatch the query to the Spark context that's on one, and not have to transfer the data to that particular node that has the Spark context. It's a modification to Spark that we may even give back to the Spark community if the Spark community believes that this is a useful capability. But it's paramount for us to be able to use Spark in that distributed multi-user way. All right, well, thank you very much for your time this morning. I appreciate it.